In lecture 22, we're going to talk about non-parametric regression for the day. And I'm not really in love with the name of this area, non-parametric. That's a really overused word in statistics and is borderline meaningless in many contexts. Nonetheless, it's a name that's used. Basically, we can view this whole area of non-parametric regression, and it's kind of an extension of some of the real simple regression models that we had learned back in the very beginning of the class. So if we recall that we assumed that in a regression problem, that our data had something like the following form. Y was some f of x plus some error epsilon. And we wanted to determine f hat so that y hat, which is f hat of x, is approximately gives us back our y, right? So this is like the main problem in the whole course. And one way that we had considered doing this, right, was we could minimize our expected squared loss. So our solution was something like minimize expected loss. This is called our risk. And so we would choose f hat to be the f that minimized, say, y minus fx squared. And our claim way back was that f hat of x is just going to be the expected value of y given x. Let's just write it that way, simply. And we had modeled this in different ways. So in order to actually get an answer for this, rather than some theoretical expectation, we had to model this expectation, something like this. And we had a couple ways to do this. For example, one being just our linear regression, where we said that f hat of x is some x transpose times some beta hat. We could work with something like polynomial regression, where if like x was just one number, so maybe a dimension of x is 1, you could say that f of x was like beta naught plus some beta 1x plus beta 2x squared plus beta 3x cubed, dot, 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 and I guess these would be hats, right? And we would estimate these things. And these models, whether or not you use kind of simple linear regression, multivariable regression, use some kind of polynomial regression, or you do some other kind of expansion here, these are making some kind of global assumption. About the form of this expectation, of this conditional expectation. another way to do this is we could work, instead of with like a global linear assumption or a global polynomial assumption relating y to x, we could work with some more local assumption. So we could basically relax this global and indeed linear assumption. And an example of this would be like k nearest neighbors regression. But broadly, this class here, which makes some more kind of local assumptions, about the relationship between y and x, right? So KNN regression only kind of works in neighborhoods. This is sometimes called, although I'm not really a fan of the word, non-parametric regression. It's an okay term, the idea being that what we're going to do is we're going to model this conditional expectation. Instead of modeling it as a linear or some global assumption, we're going to model it as some function with no particularly predefined form. It's an okay way of saying it. The idea is we're going to let the data dictate how we model this thing rather than imposing that there's a linear assumption. So something like k and n, they're kind of just letting the data tell us what this conditional expectation looks like, and it's going to depending on where we are. So these are typically more flexible models, and so all the caveats with those more flexible models come along with this. But if we have the data, or we have some justification, we can definitely use these kind of models. So in particular, let's revisit k and n regression. So k and n regression said that f hat of x was 1 over k, and then we would average, and we'd look over all I where x is in the k neighborhood. Let's back up. Let's say all n, where our training data points xn are in the k neighborhood of our point x, and we average our corresponding training y's. Right? Really kind of cumbersome to write, but it's a simple algorithm, right? You have your training data, and you have some point x you want to predict. I'm going to look at the xn's in my training data, pick the k that are closest by whatever distance metric to my x, and I'm going to average their corresponding y's. Now, the reason I like writing it out this way is because you can see that it's an average or a sum. And we can write it in some fancier ways. For example, if we let's define w n of x to be the indicator that xn is in this k neighborhood of x. So this is purely 1 if xn is one of the k closest things to x in my training data, and 0 otherwise. Now, if I write this, if I define these wn's this way, then for k and n, I can write my f hat of x in the following form. I can write it as, instead of the sum over just those things in the neighborhood, I can instead just write it as a sum over all of my training data points. And in fact, I wrote this wrong here. I'm going to say it's 1 over k times this. So it's going to be 1 over k if we're in the neighborhood and 0 otherwise. Now, if I correctly define this, instead of writing it as a sum over just things in my neighborhood, I can write it as a sum over all of my training data points. The little n goes 1 to capital N. And it's going to be Wn of x times Yn. So in this form, this is kind of the more general form, where it's the average, it's basically a sum or an average over all of my training data with some weight. So it's this thing can be interpreted as basically a weighted average of training YNs. My weight, W, for nth training pair. This thing depends on x. So it depends on the x we're predicting. And this weight is simply 1 over k if I'm in this neighborhood, if I'm close to x and 0 outside of that. Maybe I can draw a picture of this. Yeah, let's draw a little picture. So maybe here I'm going to put my training pairs in as black points here. And if I have some point, let's say k is equal to 3, and I have some point x I want to predict here, I can draw my weight function, which is going to be correspondingly basically, let's draw the weight function below. So let's say w of x. And my weight function is either going to be 1 over k or 0. And let's say for these first 2 points, it's basically going to look something like this. It's going to be 0 up until I get to the points in my neighborhood, and then it's going to drop back down. So you can visualize it kind of like this. This is like an interpolation of that, of the weight function. So this is basically a weight function. And so you can see it weights everything in the neighborhood at the constant value and everything outside of that neighborhood at 0. This kind of method, where I'm basically looking at a weighted average of the y's, this thing is called a linear smoother. So let me bring this all the way down here. This thing is called a linear smoother. And the idea is that it's a linear smoother because you basically write it as a sum or an inner product if you want. And it's just a linear combination of my training y's. It's a weighted average of my training y's. Now, so this is called a linear smoother, or k and n may be called a linear smoother. Notice here, though, that my w function are discontinuous. Right? So my weights are basically a discontinuous function in x. As I change x, my weights are going to jump between 1 over k and 0 discontinuously. As soon as my nth point gets out of the neighborhood of x, it's going to jump to 0. And so you have this kind of discontinuous smoothing in this way. We can generalize this in some kind of more smooth way, because it seems like a weird thing to call it smoother when it has this discontinuity in it. So the generalization of this is to use, let's say, nicer weighting function W or Wn, for example. And when I say nicer, maybe this thing is continuous, maybe it's differentiable, it's smooth. And in particular, if this leads to what's called kernel smoothing. Which is kind of a generalization of this kind of K and N interpretation of K and N as this kind of weighted average, but using weights that aren't as kind of discontinuous there. So the name for kernel smoothing comes from what is called a kernel function. So this word kernel, like non-parametric, is way overused in mathematics. It has several definitions just in the statistical realm itself. But for our cases, we're going to define what we call a kernel. That's supposed to read kernel. So we can say a kernel is a function K, and typically it's going to be a function from, well, let's say Rp, the dimension of our x's, to R. So it's a p-dimensional, or inputs, let's say p-dimensional real valued function, and it is positive. So the reason it's called the kernel is basically it is the important part of like a PDF of a probability density function or probability mass function, but usually density function, because we want this thing to be nice and smooth. So I've probably used this word, and you will hear people use this word in probability. We talk about the kernel of a probability density function. It just means all the important parts up to a constant, right? There's some normalizing constant, but any function that's basically positive is basically, if I normalize it, if it has a finite integral over the real line, I can just normalize this function and it'll be the probability density function of some random variable, of some distribution, right? And so it's kind of the kernel, or the important part of probability density function. Sometimes we will typically also assume that it is straight up a PDF. So if I were to integrate this over Rp, if I were to integrate kx dx, this thing would integrate to 1. So this thing is the PDF of a p-variate random variable. If it doesn't integrate to 1, but it has a finite integral, we can just take k and divide by whatever constant, and then it will integrate to 1, and it will be a PDF. You could theoretically, the reason that this is not always required is you could work with things that don't have a finite integral, like 1 over x, is not going to have a finite integral, right? That won't converge. It's an improper integral that doesn't converge. And so you couldn't actually normalize it to make its integral 1. And it's also, we typically assume some kind of symmetry. That is, k of negative x is the same thing as k of x. So this is a symmetric PDF. So you can all think of your favorite examples. For our case, basically, the word kernel is going to mean the probability density function of some symmetric random variable. And by symmetric, I mean symmetric around 0. So examples of this thing, we can just basically draw them like PDFs. Here's my x-axis, for example. I have one-dimensional x. And pick your favorite probability density function that's symmetric around 0. Oh, I don't know. Let's pick Gaussian. That would be a kernel. You could pick a triangular distribution. Maybe it looks like this. So this thing is maybe triangular. Sure. You can draw them yourself. I could pick a, uniform. This is basically a uniform distribution. But all of these could be used. And so this is the way we're going to define a kernel. Now, the reason that we're interested in kernel functions is we can use kernels to define a kind of measure of closeness. So if I have 2 points, x and y, if I look at k of, say, x minus y, this is some measure of closeness between x and y. So if I were to choose k to be well, you should be able to make the Euclidean out of this, right? So Euclidean distance, which would be x minus y, in our case, let's say if p is equal to 1, then, and k of, let's not say x, but let's say whatever argument here is just, let's say absolute value of that argument, then k of x minus y would be our kind of normal Euclidean distance here. Now, in this case, absolute value will satisfy these first two definitions. It's definitely positive, but it doesn't actually satisfy these last two definitions because that thing's not going to have a finite integral. It is symmetric, so that's good, but that won't have a finite integral. So we're probably not going to want to use that. But we could have other examples here. If k of whatever is basically a Gaussian, which is like something like this, I guess, let's say to the negative whatever squared, right? Then k of x minus y is e to the negative x minus y upon d squared. Now that thing does satisfy all four conditions for our for a definition of a kernel. So this is some kind of other measure of closeness. Notice that when x and y are equal, this thing gives us 1. And when x and y are far apart, this thing gives us a small number. So I guess our previous example here with absolute value maybe wouldn't be the best example because we really want this to be some kind of measure of closeness. So maybe I could look at like 1 over absolute value. Now that would be a measure of kind of closeness, right? When x and y are equal, this is basically infinite. When x and y are far apart, this thing is very small, right? So this first example doesn't really work because it doesn't have a finite integral. But if we work with nicer versions of the kernels, then if we look at k of difference, it basically gives us some measure of closeness. In the uniform situation, it would basically be like, are they within a certain distance of each other? 0, 1, are they within a certain distance of each other? And the triangular would be, well, you can think about what those are. The point being is that we can use these kernels to define some kind of closeness between points. And why do we want to define closeness between points? If we go back up to our nearest neighbor example, our weighting function was weighting by how close things. Now it had this neighborhood weighting function that had some okay properties, but it wasn't kind of smooth. And so you see an estimate from a k and n will kind of jump around. There can be this kind of step function that jumps around. It's not particularly smooth, which is not always the desired property. But all we need to do is our weighting function just said it's going to weight things that are close together. So ultimately our linear smoother here is a weighted average of the training y's, where it puts heavier weight on the y's that are close, or kind of y's associated with x's that are close, and less weight on y's associated with x's that are far away. And so we could define this kind of whole class of linear smoothers by just picking weight functions that weight kind of inversely with distance, or weight proportional to how close things are together. And the typical way this is done is if you have a kernel function, you can use a kernel function to define a measure of closeness, and then we can define a linear smoother, or a whole class of linear smoothers, where f hat of x is going to basically be, I'm just going to sum over my training data, and I'm going to sum wn of x times yn. This has the exact same form as our k and n, but now instead of w's, the weights being this neighborhood definition, my wn's are going to be, let's say, proportional to some measure of closeness between x and my nth training point. So the w's still measure some measure of closeness, but for example, if we were to use, for example, this Gaussian-like, or this it's called Gaussian-like kernel to define our measure of closeness, this thing is differentiable, it's continuous, and so it's going to give us a smoother estimate than the kind of step function that you're going to get from fitting a k and n regression. So this is basically the story of how you can fit a linear smoother. These things are often called kernel smoothers, and the procedure is called kernel smoothing. You pick a kernel, and you define your estimate at each point as the weighted average of my YNs, weighted by a W that is proportional to the kernel of basically the difference between the current point and the training point. So this is closeness of xn to x. So this is really just a straightforward generalization of k and n regression, but I've generalized the notion of closeness from this neighborhood closeness metric to this kernel-based closeness metric. Typically, we're going to require that the weights, if I sum up my weights, these are going to be 1. So this is one way of thinking about it. Typically require that my weights sum up to be 1, and so that's why I said this is just proportional to it, i.e. we're going to let specifically let Wn of x be the kind of kernel closeness metric between x and xn divided by all of those closeness metrics. So let's not call it n, let's call it I. Alternatively, you could think of this as we're just renormalizing the weight so that they sum to 1. This particular, using this weighting scheme, and picking a kernel, weighting my estimate at each x. Notice that my estimate at each x, the weights change. It's not like I have the same average. Just like in K and N, different x's, some things are in the neighborhood, some things aren't. Now we have a smoother version of doing that, whereas I change my x, some things are up-weighted and down-weighted in my kind of weighted average of the y's. When I do this weighting and define my weights this way through a kernel function, this is called the Nadaraya Watson, or I'm just going to call it NW, Kernel Regression Estimator. So this whole procedure is also sometimes referred to as kind of kernel regression. And doing this kind of picking the weights as the kernel of x minus xn, maybe renormalize them so they sum to 1, that's called the NW, Kernel Regression Estimator. And it's the nice and simplest way of doing this. And so the picture here is that if I have a KNN model, right, so maybe here are my training points. Let's see if I can draw these somewhat consistently across two pictures. Actually, I know I should be able to do this. Let's do a little trick here. Something like that. Okay. Now, if I can fit a K and N, and I can fit a kernel regression. So I can fit K and N regression, or I can fit kernel regression. K and N regression will, fit some kind of step function to this, right? We've seen that before. Maybe that's what it looks like. A kernel regression estimator is going to fit something smoother, and this will depend on how smooth our kernel is, for example. But it's going to end up fitting something nice and smoother, and so it's called Kernel Smoother or Kernel Regression, and is a really nice, straightforward generalization of K and N. Now we can generalize this even more into what's called local polynomial regression. So let's say generalize a bit more. And I want to do a real quick review of a couple concepts that we've hit so far, right? So if I have weights Wn for each of my data points, then the weighted average of my YNs, let's say for weights Wn, the weighted YNs is let's say Y bar W is, one way you could define it is one over the sum of the weights times the sum of Yn times Wn. So if my Wn is equal to 1 over n, 1 over capital N for all n, we get normal, typical average. Okay, so this is straight up what a weighted average is. So we can Okay, so keep that in your mind. We'll put a pin in that. If I fit a regression model, let's say our model is basically y is equal to some constant, right? Now this is basically a degenerate regression model, right? Because you could say it's some alpha plus beta x, but what if I just say it's some alpha? And I could define alpha hat as the alpha that minimizes basically the squared loss of my yn minus alpha squared. And I've said this before, we've done this I think a couple times. It turns out that the alpha that minimizes this is y bar. If I instead, let's not even change the model, let's just say instead of minimizing just the square difference between yn and alpha, I were to weight this loss function by my weights and fit this, maybe I want to do that for whatever reason, my answer here would be the weighted average. So similar deal, probably pretty easy to believe, right? As we define our weighted average above. So if I weight my loss, I minimize, I'll get a weighted average. Now, that's not a particularly typical regression model. It's kind of a degenerate regression model. Typically, we're used to something like this. Say y is alpha plus beta x, and I could define alpha hat and beta hat, of course, as the minimizers of alpha and beta if I look at my squared loss, right? Yn minus alpha minus beta xn squared, right? And these are going to be my least squares regression estimates. Nothing too surprising there. But I could also weight this thing in the same way. Something like that. And I'm going to get what's called a weighted least squares regression estimates. And so you could weight these things. And my weights here can depend on x. Or my xn's generally. So that's allowable typically. And typically they're not going to depend on the y's. Now, in general, let's just take it up one more notch, right? My general linear model is just y is x beta, right? Where, whatever, you know, this x is my design matrix. It might include an intercept, it might include a whole bunch of variables, whatever, right? And we know that if I have beta hat, so this beta has like the combination of alpha and beta. We could have a whole bunch of these, right? This is kind of the big boy way of writing it. If I look at this, and of course my loss function is y minus x beta squared. This gives me my OLS, ordinary least squares, estimate, regression estimate of beta, right? And we all should know the formula. This is x transpose x inverse x transpose y, right? But I could also weight this thing. Let's call it weighted OLS. And so instead of looking at y minus x beta, I could add in some matrix W here. And this matrix W is going to be a diagonal matrix of my WNs. And this would effectively be weighting. And I'm going to get my weighted OLS estimator. And it turns out if I write this weights as a matrix, as a diagonal matrix, so my WNs are on the diagonal of this thing, this actually has a pretty nice, simple, closed form. And it turns out it is x transpose w, x inverse, times x transpose w, y. So it turns out that we can write this thing, if that weighted OLS with a diagonal weight matrix is pretty much no harder than normal OLS, and we get an estimate that is pretty similar. Notice if W is the identity matrix, I don't do any weighting. I just get back my OLS estimator. Okay. So what the hell is the whole point of this diatribe into weighting? Weighted averages, weighted OLS. Ooh. The point being is that we can interpret our kernel regression estimator, this NW kernel regression estimator, as some kind of weighted OLS. So if I, let's say punchline, what if I consider fitting f hat at some point x? I'm going to estimate this as the minimizing value over what do we want to call it? Let's just call it theta of, and we're assuming here that x is just one-dimensional for now. What if I were to minimize this okay, so if we go back up to this, it looks a lot like this, where our WNs are this K. So let's call these our WNs. If we were to, and this is a weird way of looking at it, but we'll see how it helps us generalize things. If we were to estimate y hat as f hat of x by finding the value of theta that minimized this thing, then it turns out, as we argued above, that this thing is, say, a weighted y bar with the weights Wn being basically proportional, or being equal to, it doesn't really matter, let's just say proportional to this, right? That's exactly what we said here, is that if we wanted to solve this model and find an alpha and basically predict y is just a constant, that we just got a weighted y bar, weighted by whatever the weights were. And this is exactly the same problem, i.e. this is the NW kernel regression estimator with Wn, depending on the particular value of x, being basically proportional to this kernel of x minus xn, i.e. this closeness metric. So you can view that simple kernel regression estimator as basically solving, let's say, the NW kernel regression estimator solves a simple model, or a simple weighted regression model, where the weights depend on the x at which we're predicting, so that the weight for the nth observation at the x we're predicting at is follows our kind of kernel weighting scheme. the reason for pointing this out is that we're fitting a very simple model, right? So what we said above here is that, we started off with a simple model. We're predicting y is just some constant, right? The idea being that if I have some data points, maybe my data points look like this, right? And here is my x. What am I going to predict as my f hat of x? Basically, what I'm going to do is I'm going to just fit an average here, and my average is going to be weighted. So these are my y's here, right? I'm going to take an average of all the y's, but my average is going to be weighted towards the y's that correspond in their projection onto the x-axis to things nearby this. So it's not going to take into account these points out here very much, right? Or these points here, because their x-coordinate is far from my x. Rather, it's going to mostly concentrate on these points here because their x-coordinate is closer to the x at which I'm predicting. And so you can think of it as basically fitting some constant, right? It's like y is just alpha. So it's basically fitting, this is y bar weighted according to the weights, according to how close the x coordinates of those training points are to my x we're predicting at. But why are we fitting a constant? Why are we fitting this simple model, right? This is like equivalent to fitting this simple model where y is just some constant. Why don't we work with like a linear thing? So instead of at our point here, if I wanted to predict, maybe a more illustrative point would be if my x were over here, what would it do? It'd pick an average of y bars where it downweights these points because they're not close to this x, but it upweights these points because they are close to the x. But again, it's just going to take the average, so it's going to kind of fit that model. That's basically the constant model, right? And so its prediction is going to be like that, right? Or for my red point, the prediction is going to be like that, right? But maybe it's better if we fit why don't we fit a line here, and we could do a regression line, but we could weight that regression line to how close the x coordinates of my training data points are or are not to the x at which I want to predict. So this is like going from this simple model where y is just alpha to our standard kind of regression-like model. And so this is what's called local polynomial regression. So I think I said that. I didn't say that. So a direct generalization is called local polynomial regression. Technically, the NW kernel regression estimator is basically a simple example of that, but you could generalize it even more by fitting some kind of line, maybe that's a weighted line regression. So for example, a simple example would be to say f hat at some x is going to be, let's say alpha hat, that will depend on x, plus beta hat, that will depend on x times x, where alpha hat of x and beta hat of x are basically, we get by minimizing a weighted regression loss, squared loss, right? So if we just were fitting regression, it would look something like this. But now we're going to weight this thing using our kernel kind of closeness measure. So we're going to weight it by this, where these things are basically some WNs, and these depend on x. But we know how to do this. These things end up being the weighted regression estimates, with our weights WN being, let's say, proportional to kind of kernel distance between these things. So notice that we refit our alpha and beta at each point, right? So if I go back up to my picture, if I have my little x over here, I'm weighting these 4 points maybe highly because they end up near, they have their x coordinates of the training points are near x. But if I were to fit, at some x over here, I would downweight these training points, right? And I would upweight those training points. And so I would be fitting like you fit a different alpha and beta. And that depends on, that's highly weighted to those points over there. The idea being is we're basically fitting, like if you fit just a straight up regression line to this thing, it wouldn't do a good job because it's kind of the smooth function, but we're going to just locally adapt the regression to kind of the nearby points. So this gives us what's called local polynomial regression. So the fully here, again, we're still assuming that p is equal to 1. The way we do this for local polynomial regression is we're basically going to fit a polynomial regression in this way, locally adaptive, where we have some beta j hat at our particular x. How do we want to do this? Let's just call it beta. Is that what we want to do? Well, it doesn't really matter. We're going to solve this simultaneously. So like the collection of my beta j's is basically fit from, but it's basically just a polynomial regression. And we're going to weight, of course, like this. And then we're going to, our loss is just going to be, let's say, goes 0 to whatever the degree d of our polynomial is. Something like that. But this is just a polynomial regression, a particularly weighted polynomial regression where the weights adaptively change depending on where we're predicting. And because it's just a weighted polynomial regression, ultimately, what we're going to be able to do is we're gonna form our weight matrix W, which is going to be something like this, i.e. that. And so at some x, we form our weight matrix that looks like that, and we form our design matrix, which has in, say, 1s in the first column, my xn's in the second column, my xn squared, my xn's cubed, right? So some polynomial regression design matrix, and my beta hats, of course, follow the weighted regression, which is what is it? X transpose W x inverse X transpose W times whatever my y's are, right? But this is just some polynomial regression, and so y hat, which is, let's say, f of x hat, or sorry, f hat of x, is just going to be X transpose beta hat. And so this is, because we can write this as an inner product, is again some linear smoother. It's a linear smoother in kind of this expanded basis of polynomials. But you can fit And, so basically, instead of fitting a line, you could fit a quadratic curve, or you could fit a cubic curve, or whatever, right, at each of these points. But it's basically at each point you want to predict that, you're fitting whatever polynomial regression, and the polynomial regression to downweight training points that are far away from where we want to predict, and upweight the points that are nearby. And it does this in a smooth way using a kernel, so that we get ultimately a smooth estimate. So it will look more like this kernel regression estimate that kind of smoothly varies over the space, rather than this kind of jumping around K&N regression. So that's the deal on kind of kernel regression. The last thing I want to mention, although we're not going to have time to go into detail about them, is splines. And I'm going to do a really kind of cursory job here. But let's say kernel regression, kern, or local polynomial, regression. The idea with them is they're basically, as the name implies, local methods. So they're downweighting points that are far away from where we want to predict, and upweighting points where we want to predict. So they're basically some kind of local methods. Like a K&N is making a local assumption, or is locally modeling things. The alternative way to do this is with what are called splines. And splines are basically going to fit a better global model. So if we go back up to the beginning of our lecture, one of the reasons we like these more local methods like kernel regression or local polynomial regression is that something like a linear regression makes a very strong global assumption. It's linear over the entire space. It's not only linear at one end, but it's linear all the way at the other end. And oftentimes that doesn't work out to work very nicely. And so one of the ways of getting around that was something like K&N regression, kernel regression, local polynomial regression, where they basically just say, we're only going to model, we're not going to make a global assumption about the form of the function. We're only going to model small parts of it at a time and kind of focus that model to be local. Splines are somewhere in between, where they have a kind of better global model. And this better global model in particular is going to be piecewise polynomials. And what this does is it allows us to maintain some of the kind of local behavior. And I'm just going to draw a picture of what a spline is. So basically what it is, here's x and here's y, is it defines some points, some breakpoints, and these breakpoints are called knots. And it's going to fit between the knots, it's going to fit some polynomial. So maybe these are my data points, something like that. And it's going to fit a polynomial between the knots. So on this first interval here to here, it'll fit some polynomial. Maybe it'll fit something like this. And then it's going to, but it's only piecewise. And then on the second part, here to here, it's going to fit something else. So maybe it fits a polynomial that looks like that. But it's only a polynomial defined between these 2 points. And then this last point, maybe it fits a polynomial like that. So what it's doing is it's kind of in between, where it's defining a better kind of basis to expand the space. And rather than, if you were just fit a polynomial regression to it, that polynomial would extend over the whole x-axis. And so the behavior at one end is going to be influenced by the training points at a really far away point. And what the kind of local methods, the kernel regression, K&N, local polynomial regression, is they got rid of that kind of global assumption. Another way of doing that is by piecewise, where I'm only going to fit my, somehow the fit of my of my functional form, this we'll call a spline, which is basically a fancy word for a piecewise polynomial, is kind of locally defined because it's only piecewise between these knots. And typically, you fit some. So basically, a spline is a k degree polynomial with some condition, let's say some smoothness, at let's call it the breakpoints, or what are called the knots, these points here. So we're going to insist on there's some level of smoothness here, so you can't get anything too crazy happening there. And there are different ways of defining that, but I think that's all we're going to say on splines. There's a whole nother lecture that we could have on splines, and a whole class we could have on splines. But I just wanted to contrast that at the end, because that is the other way of getting some kind of local behavior out of a more flexible regression fit. But I will stop there because we're at time, and we can go look at some of this in the lab.